All right, this is part 2 of chapter 13. Now we're getting into meiosis. So meiosis, a lot of people call double division, where one cell divides twice, or the information gets halved twice, leaving essentially 1/4 the amount. And these two divisions we just call meiosis 1 and meiosis 2. What just happened? Oh, not what I wanted. Hang on a second. Slide jumped on me somewhere. Here we go. Okay, so here's meiosis. First we have interphase, where these chromatids have to get doubled, creating a sister chromatid. So here's our homologous pair, and keep in mind we're just looking at one homologous pair here, as opposed to all 23 pairs, if you like. This is now a diploid cell. And also keep in mind this is a diploid cell as well. The homologous pairs line up in prophase 1 and then they divide. So each cell gets one of the homologs. And then meiosis 2, the chromosome itself divides into individual sister chromatids. And this happens for all 23 sets. So in meiosis 1, you reduce the number of chromosomes from diploid to haploid. This cell here is a haploid cell. It's got one copy of each of the 23 pairs. And then meiosis 2 produces 4 haploid daughter cells, where here there's 1, 2, 3, 4, and they're all haploid. This was also haploid. All this has to begin first with interphase, and interphase only occurs before meiosis 1, not after meiosis 1. So here's interphase, all the G1, S, G2, all that good stuff. Copying, here we have crossing over potentially in prophase 1. Then we have metaphase 1, where all the homologs line up along the equator, and they can line up with red on top or red on bottom. It's just random. And then anaphase 1, they start to get pulled apart from spindle fibers. And then we have telophase 1 and cytokinesis, and we have 2 different cells here. Here you see the cleavage furrow, of course. And then the process continues. Prophase 2, here's metaphase 2, where the chromosomes line up, but you'll notice they're not paired anymore. They're lined up one on top of the other. They split into chromatids, followed by telophase 2 and cytokinesis, forming 4 haploid daughter cells. So meiosis is often compared to mitosis because they're similar processes that occur at different times, but there's 3 differences specifically that you should understand. First of all, in meiosis, crossing over can occur because the homologous chromosomes pair up. During prophase 1, that synapsis or crossing over is a possibility, and it's normal. It occurs all the time. The second one being that tetrads form on the metaphase plate. Tetrads meaning pairs of homologous chromosomes. So metaphase 1 of meiosis, the homologous chromosomes can pair up together, as opposed to in mitosis, they stack up. All 46 chromosomes line up one on top of the other. In meiosis, specifically metaphase 1, you have 2 by 2s lined up one on top of the other. And then the third one is the separation of the homologous chromosomes in meiosis 1, as opposed to the splitting of chromosomes into chromatids, which will happen in meiosis 2. Here you see the comparison. Here's what I was talking about, where the homologs pair up, versus in mitosis they line up one on top of the other. You also have your crossing over that's possible in prophase 1. Those were some of the differences we talked about. So meiosis and sexual reproduction in general helps to produce genetic variation, and that's a bonus, that's a benefit, as opposed to asexual reproduction creates clones. Different is good. It helps ensure survival. The behavior of chromosomes during meiosis and fertilization is responsible for most of the variation that arises each generation. The other potential types of variation, as you know, are mutations, which can be both good or bad, or a non-issue, just silent, if you like. But genetic variation is beneficial, and meiosis is a major cause of this. Part of the reason is because of independent assortment, where the homologous pairs line up randomly, as I mentioned previously here. Where is it? One more. This red chromosome of the pair can line up on top or on bottom, and depending on how they orient themselves, they'll split differently. And that's for each pair. That's independent assortment, where the way that this splits doesn't affect this. And law of segregation, if you might remember, was that there's a 50-50 chance that this red one will go here, or a 50% chance that this red one will go here. It's totally random. Where are we? Okay, so this is independent assortment, as I previously showed you. This is one possibility. They can split like this. Here's another possibility. giving you different combinations in the haploid gametes that you see at the bottom. And you also know that crossing over can occur. It occurs during prophase 1. Here you see where the inside legs of the homologous pairs can crisscross and exchange information, and then the information will be different, and this also leads to variation. When the gametes fuse, they'll form a zygote, and there's about 64 trillion diploid combinations. So the chances of having an offspring, a sibling, identical to you, from a different pregnancy, so let's say 1 year apart, your brother is 1 year older, the chance of him being identical to you is a 1 in 64 trillion, essentially, possibility, or more, because of mutations and crossing over and so on. So this variation is important. It's the driving force behind evolution and thus natural selection, where differences are promoted. Some are better, some are worse. We also just mentioned that mutations are a source of genetic variation, as is sexual reproduction, and we're done.